There are mysteries in the universe. We need to combine observations and theories. So I'm a theorist, so I use mathematical laws, physical laws, write equations, and use computers to do the simulations and try to understand what is going on. It's something like a detective's work, right? When you see somebody got killed, then there's a crime scene and you want to figure out who committed the crime, right? So you need to collect all kinds of information, fingerprints, footprints, smoking guns. So those are from the observational side. And from theory side, we need to use our logics. We need our physical principles. So those are the detectives part. So we connect dots and eventually figure out what is going on. So my name is Bing Zhang. I'm a professor at the University of Nevada, Las Vegas, Department of Physics and Astronomy. And I'm also the director of Nevada Center for Astrophysics. I'm an astrophysicist, which is a person who studies stars and galaxies and universe, black holes and neutron stars. And specifically, my research field is called high energy time domain multi-messenger astrophysics. So I explain these words one by one. So high energy, it means that we have very energetic objects in the universe, like black holes, like neutron stars. They accrete things, they launch jets, and they accelerate very high energy particles. And these particles can make light, not just the optical light we see. They make very energetic X-rays and gamma rays. Sometimes in the radio band, which is the lower end of the spectrum, they're not as energetic as even optical photons, but they're produced by energetic particles. So that's why they also belong to the high energy astrophysics. So time domain. If you look at the universe, you see stars and galaxies, you probably think that, okay, every night they remain the same, they're not changing. But the universe is a very active, violent place. They keep changing all the time. So especially sometimes you'll have very short duration, but very energetic bursts. Sometimes in gamma rays, sometimes in radio band. So those bursts are the ones I'm studying. So I spent many years studying so-called gamma ray bursts. And recently I'm fascinated by something called fast radio bursts. There are two kinds of different bursts and very mysterious. And so I believe that we already solved most of the problem for gamma ray bursts, GRBs. But the fast radio bursts are still a mystery. So this is most of my effort right now. So they are called FRBs. So this is time domain. And I also explained to you multi-messenger. So when we talk about astronomy, people think about telescopes, right? Light in the optical band, X-ray, gamma ray, radio. So they're all electromagnetic radiation. It's just different wavelengths. However, recent years, people start to use some other messengers, something called gravitational waves. So which is completely different from photons, but they also travel with speed of light. And the gravitational waves are generated when very energetic objects like two neutron stars, two black holes collide. So gravitational waves. And then there's another messenger which is called neutrinos. So these are also different from photons. They're leptons. They're essentially massless. They probably carry a little bit of mass and they travel with speed of light. So astronomers now are using electromagnetic radiation, gravitational waves, and neutrinos studying universe. So I'm also involved in that. I will mostly talk about FRBs, fast radio bursts, which are still a mystery right now, and there are a lot of work going on. I just came back from New York to attend the FRB meeting. So these bursts were discovered in 2007, and they're millisecond duration bursts, and they occur everywhere in the sky. And we know that they are not coming from our Milky Way; they are from great distances outside the Milky Way galaxies. But what are they produced? It's still a big mystery, and theorists have been trying to invent all kinds of models, talking about creativity. So theorists are very creative. They just look at limited amount of information. They can create all kinds of crazy ideas. And there are like 50 some different models and trying to interpret those. What we do is actually combine observations. So we collect more and more data. We try to figure out, okay, so this particular scenario, is it good or bad? And as time goes on, when we collect more and more data, but the majority of the models now are disfavored, if not ruled out. So what I did is two parts. One is I use telescopes. So I'm using a huge radio telescope, which is called 500-meter spherical aperture telescope, which is FAST, F-A-S-T, FAST. It is a 500-meter telescope in China, in Guizhou province. Probably you heard about it, right? Yes, a very big dish. I went to that position. It's a huge, it looked like a big dish, but sitting among the mountains. And you can collect the radio waves. And then we target on some fast radio burst sources. We detect a lot of bursts from individual sources, and we do statistics. We analyze the data, and we come up with some conclusions. That is one part. The other part is just to stay in my office, working with my postdocs and students, use computers. Sometimes we use a whiteboard, write some equations, and just trying to figure out what is going on. So that is the two parts of my typical research life. There are mysteries in the universe. We need to combine observations and theories. So I'm a theorist, so I use mathematical laws, physical laws, write equations, and use computers to do the simulations and try to understand what is going on. And we also need observers who are using the telescopes in all the wavelengths and gravitational wave detector and neutrino detector to collect all pieces of information so that we can digest. We can, it's something like a detective's work, right? When you see somebody got killed, then there's a crime scene and you want to figure out who committed the crime, right? So you need to collect all kinds of information, fingerprints, footprints, smoking guns. So those are from the observational side. And from theory side, we need to use our logics. We need our physical principles. So those are the detectives part. So we connect dots and eventually figure out what is going on. So as I said, I'm a theoretical astrophysicist. So what we are trying to do is actually, nothing is actually created by ourselves. So we are trying to appreciate the creativity of the nature, because whenever you discover something, then you find, oh, that the universe is so creative. Somehow we got fundamental physical laws. We have GRBs and FRBs somehow generated by the black holes. We need to figure out what is going on. So in a sense, we are not creating anything. We are actually trying to appreciate the creativity of the nature. Having said that, we are still doing bits and bits advances in order to achieve that goal. And each step actually requires a little bit of creativity. For example, if you're an observer, you use the existing telescope, you can do certain things, but you reach the limit. Then you need to have some creative idea to make a bigger, nicer, more sensitive telescope. So sometimes you need creativity, sometimes you just need money. And this is what typically astronomers are doing. They're inventing new techniques and trying to build some more advanced telescopes. And then eventually they get funding, they will build a telescope, eventually observe the universe. And for theorists, what we are doing is actually also we are limited not by the sensitivity, but we are limited by the information we collect. For example, when we look at GRBs, when we look at FRBs, we only have a certain amount of information. Initially, especially when the field just started, right? You only see a few events and you have very limited information. And then at this point, what can you do? You have to just use your limited information and then create your theoretical model and trying to figure out what is going on. And here you need some creativity. So of course, you can master mathematics and physics, astrophysics and basic principles, but how to connect those dots need some creativity. So that was why there were 50 different models when the FRBs were discovered. Of course, most of them are wrong. So the successful ones actually require a little bit more creativity and sometimes a little bit more critical thinking. So it's not just try to create an idea. It's easy to create an idea, and most times it is wrong. And what is needed is, besides thinking about new ideas, you need to use the information you collect and just ask yourself, criticize yourself. So am I doing this right? And a lot of theorists, they don't ask this question, and after a few years, they turned out to be wrong. So we are trying to be on the right track, but occasionally we still make mistakes. But this is the fun of research. So we need people from different backgrounds to work together. As you said, we need people to build telescopes. We need people to take data. We use computers. We require very good computers and very good algorithms. And some people are sharing algorithms. And these days we are using machine learning, artificial intelligence technology, which is very helpful for us to do classification or imaging or identification some new signals. So yeah, so it is definitely a interdisciplinary research field. In the maybe centuries ago, one can still use one person's mind, like Albert Einstein, just sitting in his office and think about problems in 1 year and can write 3 most important papers. But that stage already passed. So we already reached, so for understanding the fundamental physical laws, so we need to go to the largest scale or the smallest scale. In the smallest scale, that's say particle accelerators. We need to spend a huge amount of money to build accelerators. In the largest scale, like astronomy, astrophysics, we need to build huge telescopes or detectors to study the universe. So nothing can be done just by one person or just one mind and sitting there doing nothing and just to think. So the science is already developed to the stage that new frontiers require new discoveries, and new discoveries need new telescopes, detectors, accelerators, and need more funding. So definitely funding is very essential to keep science going.